Okay, now that's okay. Well, I mean, we can start now officially. Thank you for your interest in this class. So this is the first lecture of Colloidal Science and Nanoscale Engineering. Welcome also to our distance education students who are going to watch the class a little bit after us. The first thing about this class is that I'm very happy to see here people from different disciplines, not only from chemical engineering. And this is really, I think, very positive, and this is what this class is about. Now, I have to make the statement that this class reflects my interests, scientific research interests, interests in academic development, a lot. And this is because I come from a background in colloidal science, and I would like to go into nanoscale engineering. Now, nanoscale engineering is a little bit underdeveloped discipline. We're going to discuss this a little bit later. But certainly, we would like to start from colloidal science and go into nanoscale engineering, be more familiar with the new concepts in this field. So this class is going to combine both fundamental and applied aspects. And the applied aspects are going to be the ones which are going to really bring us into some of the interests in today's technology. And these interests are essentially come from a variety of disciplines. I'm glad that we have some electrical engineers here, material scientists, paper scientists, and so on. I mean, this is really very positive, and that's where the science is going these days in general. When it comes to this class, what I would like to do is really not just make the unload material on you and then you get the credit. I think it would be a good experience for both of us if we could make it a bit more lively, interesting, discussion-like, and so on. Which is not only my what I could do. So just feel free to interrupt me at any moment and ask questions. Be a bit provocative if you like. At some point, we're going to have a few discussions in this class, and you can also participate even in a way in the teaching activity of this class. But don't hesitate to stop me at any moment and ask questions, suggest something, tell me what you're interested in, and so on. Now, this is the first lecture. Usually, we have to do the logistics of the class and go through the plan. Now, I'm going to do that, but before I do that, I would like to first even give you the material of the lecture, which will be introduction to different types of colloidal systems, why you are interested in these systems, and what we can do with colloidal, with colloidal and nanoscale engineering. So, if you feel that you don't know exactly what we're going to do and when we're going to do it, just wait a little bit. Towards the end of the lecture, we're going to discuss that. But before this, let's see what colloidal science is about, what types of system we study, and so on. So, now what is this? Well, actually not. I mean, it's really a colloidal system. Now, I'm sure that you know what type of colloidal system is, and you have seen it a lot. And that would be... Water? No. I mean, it has water, but it's not all in water. But it's close. Soap. Well, soap is a bar of soap. I mean, that's obviously not a bar of soap. Well, that but it's that's warmer. Soap bubble surface. Sorry? The surface of the soap bubble? Yeah, it's not actually, I don't think this is the surface of the soap bubble, but this is a free foam film. Now, it looks very nice, but then it poses also a variety of questions. Now, why would this free foam film, first of all, why would it have these colors? Now, second of all, why would this film have two regions? One region is where it has these intensive colors, and another region where it has this totally black color. And now, if it looks black, why doesn't it reflect light? What's the problem with the film when it's all when it's black and actually it's all thin? And then the question is, why do you get this film when you use water and soap? And to be precise, in colloidal science, this is surfactant. And one don't you get the same film when you just use water? I mean, I'm sure that some of you know the answers of some of these questions, but I hope by the end of the class you know the answers of similar questions, and in more new technology areas than that. That this is what we're going to study. It has beautiful applied aspects. I'm going to try to emphasize them. It has lots of formulas. We're going to try to make you learn these formulas without too much trouble, but you have to go through these formulas too. That will be a bit later, not today. Now, the fact that kind of like colloidal systems have these interesting properties has been known for a long time. Colloidal science is by no means a new science in the sense of fancy exactly this day. People have been doing colloids since maybe 2 centuries ago. And by the middle of this century, the fundamentals of colloidal science were already established. We have to go through these fundamentals in order to know what we'll be doing in the class. But what we also have to understand is how we can apply these fundamentals to new interesting systems on the nanoscale these days. So essentially, colloidal science is having a revival today because it has applications in a variety of new areas. And all these new areas somehow relate to the famous fancy word nano, which we're going to use a lot. But kind of colloidal science are really not only or exclusively on the nanoscale. So this is kind of like bits taken out from a book. This is kind of the scale of dimensions where we'll be working, that we'll be using. And kind of in this case, people have outlined a variety of colloidal systems. Now, this is just if you take general colloidal particles. Kind of the nanoscale really covers the region between 1 nanometer and 100 nanometers. And then there are some people use the term mesoscale. All of that scale is covered in colloids. Now, where on this scale would be 1 millimeter? If you extend the scale, you can see that this is a logarithmic scale, like every division is 10 times larger than the other. So we have a 100 nanometer here, so the next division will be 1 millimeter. By your eye, you can see objects which are about somewhere here. So then we start dividing the scale by tenths and tenths. 1,000 of 1 millimeter is 1 micrometer. And 1 micrometer is really kind of like somewhere of useful dimensions in what we're going to study. We divide 1 micrometer in 10. We go to 100 nanometers. We are already entering the fashionable nano world. We go down to 10 nanometers. Eventually, you can think of some systems which are as small as 1 nanometer. And then what would be below a nanometer? What objects would be below a nanometer? Molecules. Simple, plain molecules. And we're not going to study this. So most of the systems that we're going to study really cover the range between 1 nanometer and 10 micrometers or so. Now, this is not exactly a definition of a colloidal system. We'll go through this a little bit later. Now, what I have made in the next few slides is kind of I have outlined a few general colloidal systems for you, some of which are certainly familiar. And the most classical system is surfactants, or as some of you would say, soaps. Now, the surfactant molecules have the kind of important properties that they have 2 regions of the molecule, one of which has a totally different properties than the other one. Now, if you take oil and water, one of the parts of the surfactant molecule is going to be the one that loves the oil. The other one will be the one that loves the water. So we're going to, of course, to go through surfactants a little bit later, kind of describe what is the chemical nature of those sides of the molecules and so on. The point is, now what happens when you have these 2 kind of different molecules, different types of the molecular structure? Now they kind of don't love each other, but they may come to love similar parts from other molecules. So they say, okay, I mean, I don't love kind of my twin brother on the other half of the molecule. But if kind of I have another type of molecule like that, I'm going to like the surfactant side of the same type. So that's why these simple molecules would self-assemble themselves into a variety of structures, some of which are shown here. So if you just put them in water and start increasing the concentration, you are going to see that the surfactants would self-assemble in these structures which are called micelles. You are going to see that they self-assemble in a variety of rod-like structures, variety of layered structures. Again, the thing that you can always see is that the same types of the molecules are facing each other. Kind of they get together because they would like to kind of minimize the energy by getting the same types of the molecules together. And there are some even more exotic structures, inverted micelles. You can see that this is eventually this one structure if you kind of invert it from inside out. There are these cubic structures and lipid bilayer structures and so on. So you have a variety of these types of molecular assemblies. And you know the basic properties of surfactant, which you use every day, or at least like many times a day. And this is that when you put it in water, it decreases the interfacial tension and it has detergency, which we're going to discuss a bit later.
I noticed you say you're going to put it in water and then decrease the concentration. What does decreasing the concentration have?
Well, I mean, if you have lots of surfactant, it would form many of those structures. But if you don't have this much surfactant, it's not going to form a self-assembled structure in the middle, but it's still going to go to the surface and have these surface active properties. So when you have lots of surfactant, you know what you have. You can observe this actually in your bathroom. If you leave a soap in water, it gets to be a gel. The gel is actually an extreme structure of this type. But if you just use a little amount of surfactant, you know that it washes, it forms bubbles, and this is because it absorbs on any surface, decreases the interfacial tension, and stabilizes the system. Certainly you're going to go through this a bit later. But the point is that you can take a molecule, you can put it in water, and this molecule is going to kind of self-assemble into a variety of structures. Or then you have a variety of other molecules too. Now, polymers tend either to absorb on surfaces, and I'm certain that here we have quite a few students of the polymer class of Jan Genzer who know about all those loops, trains, and other structures which a polymer molecules form on surfaces. A polymer molecule can just also dissolve. Now, depending on the properties of the molecule, we're going to go through this very briefly. It may form some kind of tangled web, which is essentially in a way a particle in itself, right? So you know that when you put polymer molecules in solvent, if the molecules are not well soluble, it's going to look kind of cloudy. And the cloudiness comes because the polymer molecules form colloidal particles. And then there is the extreme, not the extreme, but very important case of polymers which comprise our bodies, and these are proteins. Now, the protein is essentially a biological polymer. It has specific properties, it has usually specific structure into which it has assembled. And the point about these biomolecules is, if you think about this, it's a colloidal particle too. So if you want to understand how proteins in solution interact with each other and so on, you have to know colloidal science. And this is the other kind of important applied aspect of colloidal science these days, application in biological sciences. One of which is understanding how biological molecules interact. The other one, which I'm very interested in itself, is using this in different types of sensors and bioarrays, understanding what makes a biological molecule come to some specific place. So you can use this for detection of this molecule and eventually detection of diseases or whatever application related to biology. And again, in terms of self-assembly, now that's for Shalini over there specifically. Now, if you take lipids and if you take proteins and so on, you have kind of very, very important structures of biological membranes. The structure, the surface of any biological cell is a very complex self-assembled structure which has lipids, which has proteins, which has glycoproteins and so on. So nature can assemble, self-assemble structures which are much beyond what we can do so far. On the other hand, if we know colloidal science, hopefully we'll be able to do this someday. Now, the simplest, easiest least expensive in many cases type of colloidal science would be just particles, pieces of solid material dispersed in the liquid. And here I have kind of taken some examples of different types of particles. Now, latex microspheres, now these are particles which have been dried and they have assembled into this structure which some of the attendees here are actually studying. You can take polymer droplets, polymerize them, so instead of a droplet you have eventually polymer spheres. If these spheres are microscopic, they form a colloidal suspension which is called latex, and which is the one that you use to paint the walls. When you paint the walls, these particles come together. They may even merge together and form the coating on the wall. In some cases, for research, you can obtain these particles as this very monodisperse, very uniform in size suspension, which can be used for research. Now, this scale bar here is 1 micrometer. So you remember where 1 micrometer stands. It's on the high side of colloidal science. Now, you can see these particles here, which look kind of like the other ones, maybe if you enlarge them. But then these are gold nanoparticles, and actually this is an image obtained from Brian Privo over there. And if you take a look at the scale bar here, this scale bar is 100 nanometers. And the nanoparticles are much smaller than that. So eventually you have more or less the same particles, at least in size, in shape. Yeah, at least in shape, but the size here is different by a few orders of magnitude. So there are technological processes which allow you to make such particles all throughout the size range that we have kind of just noted. You can make similar spheres from semiconductors by using different types of chemical deposition processes. Or then you can play with different types of particles. Now you take, let's say, this and these particles. You take the large particles and then crush them into a cover of the small particles. And what you get here are these they're called raspberry particles here and of this type. And now this was state of the art in particle synthesis maybe 20 years ago. Now these days, because of the applications of the nanoscience, people are getting to make even more complex nanoparticle suspensions. So these are some examples from the recent literature. What you see here are metallic nanoparticles. Again, you can see that they're relatively small, not as small as the gold particles that we saw on the previous slide. But what you can see is people can make them like ideal cubes or different types of octagons. Or you can make a variety of kind of triangular shaped pyramids and so on out of these particles. And by modifying the process, you can obtain even more, let's say, complex shapes. What you see here is obviously rod-like particles. Now, these are very special rod-like particles. We're going to come to it a little bit later. These are very long, fiber-like particles. All of these are types of suspensions. All of this would be solid particles which you can put in liquid. You can make them very thin and very small and very large. And kind of, I mean, like especially electrical engineers may have heard of one type of particle which is very important like that, which would be what? I mean, you have certainly, everybody has heard the name. Kind of, I mean, like the one, yeah, carbon nanotubes. But you don't really need to use carbon nanotubes. I mean, you can make them from semiconductors and from a variety of other chemical compositions. And now if you take a look at this image here, it depends a little bit on how well you can see it on that screen. But kind of you can see that these particles are a bit weird. They are kind of yellow on both sides, and then they are white in the middle. Yeah. So these are special this is an example of engineering. These are special types of particles which kind of have, in the middle of the rod you have silver, and on both sides of the rod you have gold. And these days people can even use these particles as what they call colloidal barcodes. You can kind of like make them kind of like line the silver and gold in many layers, so it looks like a like a barcode, the ones that you have on the products when you go to the supermarket. So people would think, I mean, I can't guarantee that this is going to happen, that you can make such particles which you can use to kind of like put a barcode on a living cell, for example, or even on a molecule.
What's the scale on those?
These ones would be, these ones are large. Kind of, I mean, this hadn't had a scale in the paper, but I guess it will be about 10 times this one. This is 1 micrometer. So this will be about 10 micrometer on that. This will be about 10 micrometer scale here. So they're really not that small. On the other hand, I mean, there is quite lots of room to go down the bottom, right? The famous kind of like phrase of Feynman, who started the nano kind of like field long ago, is that there is lots of room for growth towards the bottom. So kind of, I mean, maybe I wouldn't be surprised if people make these particles smaller. And actually, some people are doing that. I mean, I know a few people in Caltech, for example, who are working in making this very small. And then something more traditional, and something on a larger scale, and something that you have already all seen. Kind of, it may not look as fancy, or it may not look as nano, but this is very important for practice, and this is foams and emulsions. I mean, people may not make much money yet of nanoparticles, but all companies, which you know, kind of large corporations, are making lots of revenue from making different types of foams and emulsions. And you certainly know some systems like that. I mean, like obviously foam would form in itself every time, but many of the consumer products are either foams or emulsions. Now, what would be characteristics of those? You have either water or air inside the bubble or the droplet. Then when you press them, they have this thin lamella, which are called thin liquid films. And then you have these 3-phase contact angles. A single one would be called meniscus. The many would be called menisci. So kind of, I mean, the liquid inside here would be distributed inside the films, and then it would flow through the 3-phase boundaries, through the meniscuses. Now, kind of, I mean, let's give some try to kind of, I mean, some consumer products here. Now, okay, you already know that if you buy a can of paint, this is likely to be latex. Now, what would you have inside, let's say, kind of like you have margarine, for example, which is not the favorable kind of diet food these days, but what's a margarine?
Little water emulsion.
Well, it's kind of, I mean, it's very close. I mean, it will be oil in, it will be water in oil emulsion. Okay. So you can't eat fat as such. But if you put some water inside the fat and disperse it in small droplets, you get something that's edible, which is margarine, for example, or different types of spreads. Now, a spread or a mayonnaise would be what? It's not oily, but it has oil inside. Right, it would be oil in water emulsion. Now, and my kind of favorite tough question is, what is ice cream? We get somebody from, yeah, she should know. Huh? Yeah, well, I mean, you have all droplets inside, right? So how it can be formed with droplets? Okay, so the answer is it's a very complex system which has, I mean, inside an ice cream you have essentially air, you have oil, and you have water, and you have ice crystals. So the continuous phase is more or less water. But you have ice crystals, so it's a dispersion because you have solid crystals inside. You have oil droplets, so it's also an emulsion. And you have air, so it's also a foam. So essentially it's kind of like foam, emulsion, and suspension together. And obviously, in order to make ice cream, I mean, you need to know colloidal science, which is actually what many people in this area do these days. So kind of, I mean, this is the kind of another type of, this is really a classical type of colloidal system. People have been studying this for years. My research, actually, graduate research was on emulsion stability and so on. These days, people are more interested in nano, but other people are making money out of that. So hopefully you know how to make both at the end of this class. And now we come to other types of colloids. I mean, it's a bit too complex to make examples here. So what I have made is I have just listed different types of thin films and self-assembled monolayers. We're going to go back to this area. We're going to study what happens when you cover a surface with a very thin layer, how you can cover surfaces with very thin layer, how you can modify the properties of surfaces by this very thin layer, and so on. The point is the thin layers and self-assembled films are important. Now you have already seen a variety of gels. Mesoporous materials would be again like a variety of systems that you see around in consumer products. We're not going to go into too many details about that, but you because what we want to know the basics rather than applications. We want to understand the fundamentals. Now, before I go to the most the final and most controversial part in a way, there are other types of colloidal systems which you won't study here at all. And one type of system is, for example, you can see it around you eventually from time to time. You don't like it too much. Now, what is fog? Yeah, I mean, it's small water droplets in air. This is a colloidal system which is called aerosol. And you have heard about this. I mean, we're not going to study this. This is not that important from the viewpoint of what that we want to put on that class. But you have to be aware that you can have a variety of other systems. You can also disperse solid particles in air, which is something that you don't want to do because this is contamination. And finally, the present state of micro and nanofabrication, electronic technologies, and so on allows these days to make elements which are as small as this. So this is an example of what's called MEMS, microelectromechanical device system. This is a small device which has logs, different types of gears, and so on. We're going to go back to these devices towards the end of the course and discuss their potential applications and problems. But even before we do that, you can easily notice now this is a flea or something like that, the usual microscopic animal that people would like to put on top of the devices, just to show how small they are. Now you have this which is so small, it's obviously in the colloidal size range. So people have not classified these micro devices and nano devices as colloids yet, but in the view of where science and technology are going, I think they very well deserve to be classified as part of colloidal science. Now this has a variety of implications. The first implication is like that. Now you're a mechanical engineer and you know how to design gears. And you know how these gears work. So you design large gears, you can design smaller gears, and you can keep designing smaller gears, and these days you have the technology to make them colloidal-sized gears. And people have done this, and they have been very, what do you think, happy or disappointed? Happy? Now that's Daniel over there. No, actually they were very disappointed. And they were very disappointed because these gears suddenly start sticking. They have all types of problems. They wear themselves at enormously fast rate, and so they don't operate like regular gears. And the reason why they don't operate like regular gears is because you can't treat a system which is this small without understanding colloidal science and colloidal interactions. You have to treat them as colloids, and there are different types of forces, different types of interactions which operate in the colloidal world than the one that you can see in a macroscopic world. So this kind of concludes the overview of different types of systems. Any questions about the colloidal types of systems or the classification or something like that? Okay. Now, I mentioned that the colloidal system is generally different from other types of just mechanical systems. Now, what makes a colloidal system different? Now, we have already seen that one thing is the size range. Now, you don't look at your handouts there. Now, one thing is the size range. Now, is the size range the primary thing that makes a colloidal system different or not? Now, okay, or kind of to put this question in another way, if you put rice in water, is this a colloidal system or not? Why not? It's just a bit scaled up, right? Well, yeah, I mean, what happens when you scale it up? What's the difference between rice in water, for example, and let's say latex microparticles in water? You know that kind of okay. Huh?
Because the sensing, it's not different.
Yeah, well, it's kind of the reason is like that. Now you have rice in water. I mean, first of all, it falls down immediately, right? And latex in water stays for a long time. It falls down eventually. Now, if the latex dries on the wall, I mean, you cannot peel it out, but you can kind of, I mean, if you spread rice on the floor, you can pick it up. So the real difference kind of like between these two systems comes from not from the size, it comes from the kind of, you know, like, I mean, you have heard probably that whatever you do, kind of thermodynamics kind of describes everything. So you kind of come to thermodynamics. And now there are many definitions for colloids. I mean, I don't say this is the most kind of truthful one. But really, when you think about what is important, you should think about thermodynamics. And kind of, I mean, it's a long sentence here, but colloidal systems are the ones where the macroscopic properties are determined by the action of intermolecular forces on the micro scale. So there is something which acts inside the system, which determines its properties. It acts on such a small scale that you cannot see the action of the forces themselves. You can only see the macroscopic kind of side of these forces. And the macroscopic side would be that either you have something that's stable or something which collapses, precipitates, something that kind of may form a very well organized structure, or something that doesn't form a structure at all, and so on. So the real kind of, again, like the first point, kind of, I mean, this should be a little bit also of a kind of direction towards the later parts of the course, where we're going to discuss interaction. The real kind of thing that makes the colloidal system different is the interactions. Now, this is not the only one, because kind of the interactions are related to the size. The size itself is not that important, but because small size determines large surface area, and the interactions acts across different areas, right? I mean, kind of, I mean, if I make my hands interact, I mean, that is not this much because my hands are small. If my hands were 10 times bigger, I mean, the clap would be 10 times stronger, perhaps. The point is that it's related to the size. So we're going to kind of, I'm going to demonstrate the effect of the size kind of in just a few transparencies. The point here is that kind of, I mean, like, what makes the colloidal systems different is that you have intermolecular interactions which act on that scale. They determine what the system do. And I'm going to kind of go through this in detail. We'll kind of explore how this works, and we will explore how we can use this in nanoscale engineering. Now, kind of I was a bit kind of like unhappy to let you go the first lecture without a few formulas. So I have included a few formulas here. Now, this is more or less for your kind of, I mean, just for kind of just understanding how you describe colloidal systems rather than something that you need to memorize. Now, you will not need to memorize anything in this class. What I would like you to do is kind of course, have the notes and have some kind of like understanding how it works. And when it comes to tests and so on, I mean, it's going to be, of course, you can use any source that you like. Now, typically, the suspension of colloidal particles would not be monodispersed in size. So, kind of, I mean, let's say you're inspired by colloidal science and you would like to do some experiments at home, and you want to buy some lattice spheres in suspension, and then you kind of like have to ask a producer exactly how good these spheres are and so on. Now, the first thing that would be kind of relevant in this case is the distribution of the sizes. And you make this distribution by counting the number of particles within a certain size range, and then plotting this on a histogram. Now, you usually know that kind of in many probability phenomena, related phenomena, this histogram, the shape of that histogram would be what? Right, or kind of in terms of probabilities, this is normal distribution, which is kind of shown here. You have the average size being right in the middle of the distribution. Now D, this one here, D with the overline is the average size. What this formula tells you is that the further a certain kind of like a certain size is further away from the average size, the less you have the probability of having a particles of this size. The width of this distribution is determined by the parameter sigma, the width of the distribution. It appears also here, and you have the normal distribution. Now, you can obtain, for colloidal suspension, you can obtain these types of distribution by using a certain instrument which measures size distributions. One such instrument would be light scattering equipment. And somewhere later in the class, we're going to go and just examine how light scattering works. Now, there is no reason that any colloidal suspension should have a normal distribution. And actually, what happens if you make an emulsion is you very often get what is called log normal distribution. Now, in a way, this is unique for colloidal systems. You know that for probabilities, you only have kind of usually normal distribution. Now, in this system, essentially, you're going to have a normal distribution, or more or less a normal distribution, if you plot your particle size on a logarithmic scale. Let me see which was... Anything happening? No. That's not the right one either. Okay, I forgot how. Okay, no, that's fine. We cleaned it. So the point is that kind of if you plot it on a logarithmic scale, you're going to have normal distribution, but actually this is a logarithmic size distribution. Now, this is, of course, if you are in production of colloidal suspension, this is one of these two parameters, the size, the average size, and the size distribution, are very important for characterizing your product, whether it complies with specifications or not. Now, something that needs to be made aware of here is that you can have, now if you have a system which is not monodispersed, which has certain distribution of sizes, you have a variety of average diameters. And I have illustrated this here. Now, what would be the total surface area of such system? You get the total surface area by summing over all groups of particles times the particle surface. So if you sum the surface of all particles, you're going to get the total surface area. Now, then you can say like that, okay, now imagine that I substitute this system with a system which has the same surface area but has particles of single size. What you're going to have in this case is that the size of a single particle would be equal to this surface area divided by the number of particles. Now we go one step further and say, okay, so let's say this is my surface, my diameter, which is kind of surface kind of average surface by average surface area. This is called surface surface area average, which is defined like that. Now, this is not the same as the average diameter if you just take the diameters of all particles. It is different. And in a very similar way, you can have an average diameter by particle volume. So you can have an average diameter by particle size, by real particle diameter. You can have an average diameter by particle surface. And you can have an average diameter by particle volume. So let's say, what is the particle with the average volume? What is the diameter of the particle of the average volume of the system? And these are not the same. Now, we're not going to go into many details here, and we're possibly not going to go to that topic back later in the class. What I want you to be aware of is that average particle diameter also comes with a string attached. And this is that you don't know exactly which of it is. I mean, like, you should know, kind of like when you take the specifications, you should know whether this is the average by particle size, average by particle surface, or average by particle volume. And they're a little bit different. Now, let's say like that, kind of, I mean, like, this is an example which I have made myself, kind of out of kind of the surface area. Now, you're going to have a homework actually, which is going to be very simple calculations of surface area. Now, you take a sphere of radius 1 centimeter. Obviously, you have one sphere. You can calculate the area of that sphere, and this is going to be kind of okay. That's the total area would be this one. So this sphere is going to have an area of kind of much less than kind of a square meter, obviously. So it's almost insignificant surface area. Now you take that sphere and start dividing it into smaller spheres. So you keep the volume constant, but then you kind of cut the sphere into spheres of 1 micrometer. Then you cut it into spheres of 100 nanometers, and then into spheres of 10 nanometers, similar to the particles which you actually saw on the photos. Now, what happens now? The number of spheres increases drastically because every particle is so small that kind of when you have to make small particles, you have to cut this one particle into many more and more particles. The area per sphere decreases drastically because kind of, I mean, obviously you have these small spheres, the smaller it gets, the smaller the area per single sphere. Now, however, if you go back and say, okay, now what was happened to the total area of the system which I started distributing, now take a look what happens here. Kind of, you have started with something that's very small. You kind of like the centimeter sphere has a very small surface area. Now, when you go to the 1 micrometer spheres, the total area of all 1 micrometer spheres is already about kind of 12 square meters. You keep cutting the particles and you have 100 square meters for 100 nanometer particles. And then you make them like really nanoparticles, 10 nanometer particles, and take a look at this surface area. This is 1,000, more than 1,000 square meters. So which means that you started with a particle which was just 1 centimeter in diameter. You cut it in these smaller particles, and suddenly you ended up with a system of particles which has a surface area which is the equivalent of, let's say, the 5 average house kind of floors combined. You can cover a basketball field or something like that. So if somebody tells you that kind of, I mean, there is nothing that important when it comes to nanoparticles, I mean, you know that the interactions are important, even though we have not discussed how. But you can immediately tell him, okay, but take a look what happens to the surface. I mean, just 1 cubic centimeter of material, when made into nanoparticles, has an area of a whole basketball field. So that is one of the reasons why people are discussing nano so much. Of course, the other reason is when it comes to microscopic devices. Now, are these systems thermodynamically stable? The typical colloidal system. you can, the truth is that you can actually have two types of systems. The general name is lipophilic and lipophobic. Now you usually work with water, so for water, lipophilic would be the equivalent of hydrophilic and hydrophobic. Lipophilic is a system of particles, molecules, colloids, which in a way like the environment, the energy when you put this molecule in the environment, essentially you release energy. This is a thermodynamically favorable process. Now lipophobic are particles, are colloidal systems, which don't really like the solvent. You know that water doesn't like oil. So if you try to disperse oil in water, you're not going to have oil droplets which love water. And this is the reason why these droplets would like to separate and turn back into oil and water. Unless you add surfactant or something that stabilizes the system, it's going to separate. Now, does this mean that all hydrophobic systems are unstable, in your view? Any ideas?
Physics.
Right. Is it stable or not?
Yeah.
It is. Right, but there is even more drastic element here because human bodies are actually mostly hydrophobic lipid. And obviously we're not unstable, at least for certain number of years. So the truth is that there are many colloidal systems which would like to separate if you just follow thermodynamics, but they are kinetically stable. So they can live forever just because the interactions between the particles don't allow them to really aggregate easily. So if you aggregate the particles, they're going to fall down and never come back. But this is if you aggregate them. If you don't allow them to come together, if you don't press them, if you don't change the environment and so on, they're going to stay dispersed forever just because they're kinetically stable. They have to go through a thermodynamic barrier, which is usually too high for them to go through spontaneously. Lipophilic systems would be different types of surfactants, proteins, and so on. You can disperse them, you can dry them, you can put water, they're going to redisperse again. So you can repeat this process really forever, and you can repeat it. Now that's the difference between lipophilic and lipophobic, is that lipophilic are reversibly, you can go from particles to suspension and back, while lipophobic, hydrophobic, once you allow them to separate, they will never come back spontaneously. Now, I have been teaching thermodynamics a year ago. Now, in this case, which of those elements here in the Gibbs potential is important? Which separates lipophobic and lipophilic systems? Yeah. If you haven't been in my class, and nobody from my class said that, so that's not good. No, joking, of course. Sure, this is the interaction between that's where the interaction between the particle and the solvent gets to, right? Entropy is the one that changes the interactions. Entropy would always like to disperse the particles. For entropic reasons, any system of particles would like to be as chaotic and dispersed as possible. The difference here is the enthalpy between the two systems. And finally, this was supposed to appear like in parts, but anyway. Now, when you consider kinetic stability, we have to consider particle-particle interactions. So we don't consider the whole thermodynamics of the system. We consider only how the particles interact by themselves. Now, we don't have a device in the lab which is called interactometer, because we can't measure interactions directly. So what are the properties of the system that we measure, and how do we characterize colloids? You measure the surface charge. You can measure the surface properties. Or you can measure, for example, different other parameters like the osmotic pressure. The osmotic pressure of any system would have the ideal component, and would have this second virial coefficient here, which is there because the particles interact with each other. So if you measure, and this is why, for example, like for protein solutions, if it's very difficult to measure interactions between proteins because they're so small that, I mean, you cannot measure the surface charge immediately or properties. But what you can do is you can measure the osmotic pressure, and this is the way biological measurements are often made. And now when we speak about stability, we also have to discuss kind of what types of destability, destabilization you can have. Now you can have reversible flocculation. Now this is just kind of, you have certainly heard these names, but kind of, I'm not sure that everybody knows exactly what is meant by which. Now you have heard about flocculation, aggregation, and coalescence. Now what is the difference between those three? In a way, all of them means kind of something is not that stable, right? So what is the difference between these three? In the flocculation, you can have particles which come together, but this is reversible. So you change the conditions and then they disperse again. Aggregation in general would be irreversible, so they come together and never come back. Now, what types of systems would have flocculation and aggregation? From the systems that we discussed, just on the previous slide. What were the two systems that we just discussed a while ago? You can have it. Right. So which of them is kind of flocculates and which aggregates? Right. Yeah. I mean, the hydrophobic systems would like to get out of water, so they get together and never kind of like separate again and so on. And coalescence is a term which is used in the case of emulsions, where kind of what happens is the two droplets come together, and then they kind of really join kind of their volume, so you have one single droplet. This would be coalescence.
Is aggregation and coalescence the reason that you get the log of normal distribution?
Actually, the reason that you get the log normal, it's kind of like what happens is kind of you disperse them, they come back and so on. Typically, you get log normal distribution when you start kind of breaking things into smaller objects. Sometimes some of the objects can come back into larger ones. So that's why they essentially kind of some of the particles would go back to larger objects. So that's why essentially the log normal distribution actually has heavy tail. Kind of it has lots of large particles. So that's why typically for emulsions, when you start breaking it, you can have very small emulsion droplets, but some droplets are going to coalesce back, and that's why you have log normal distribution. You have lots of large droplets in an emulsion. So that's kind of, quite precise. Now, we can go, about just a few kind of like pep slides about nanoscale engineering. Before that, however, and kind of this is a question which is not for the people who have attended my thermodynamics class last year. Now, if you are studying the interactions between two particles, now you have the formula, you know the parameters, you plug it in the formula and you get some number. And typically you get a number which looks like 5 times 10 to the minus 13 joules, which is very small number in joules, and kind of, doesn't tell you anything concretely, right? Kind of, some energy. Now, what is the criteria in order to kind of, evaluate how large this interaction parameter is, this interaction is? You have studied this in, the ones of you who have studied thermodynamics, molecular thermodynamics, and so on. There is a very important parameter which is used to kind of evaluate particle-particle or molecule-molecule interactions and so on.
Pair potentials.
Right, pair potential is the mathematical function which you use to calculate it. But on what scale do you put it kind of in order to understand whether it's important or not? I'm going to discuss this a bit later, but I want you to be aware of this kind of like this very important kind of evaluator right now.
The Lennard-Jones parameter?
No, it's kind of, yeah, it's a Lennard-Jones parameter. It's a parameter. Now you get the energy, and what you compare this energy against. How do you know, is it important or not? Now, have you, okay, I know that you know, so don't kind of, so have you made something that is, which is, let's say, a very small interaction, or is it like the equivalent of a nuclear explosion if you make the system large? Okay, I mean, like, okay, somebody who has taken my class? Yeah, KT. So it's kind of the Boltzmann constant times the temperature gives you kind of the average thermal energy of any particle, molecule, or anything in your system. If you have an energy of interaction between two molecules, particles, and so on, which is comparable to KT, this means that it's important. If it's more than KT, and KT now, okay, you can say like, I mean, what's that? I mean, it kind of, I mean, it looks like some parameter multiplied by the temperature. Why I was speaking of energy? It has units of energy, and actually, it's so important that kind of like for the problems that you may have to face and so on, actually good people like the author of the textbook here is Revashvili. If you go to the first page, actually he has kind of saved you from the trouble of calculating that. So we have the value of KT, no different types of units that you can think of. And the reason you have it here in this table is that it's so important. I mean, this is really the scale on which you put all thermodynamic interactions in colloidal systems or in molecular systems and so on. Okay, so far with these formulas. Now, there is one question which I think is important to address here. And this is kind of, I mean, like this class is called Colloid Science and Nanoscale Engineering. Now, 10 years ago, these classes were called Colloidal Science. Now, how come that we have nanoscale engineering, apart from the fact that we need to also get grants as scientists? Now, what is the reason why these days you have the nanoscale engineering aspects of our research or technology? And I would like to address this because this is something which is going to emerge through the class. Now, we have a variety of recent technological developments which has allowed an unprecedented degree of control of your system. Now, the first two, which are fairly much done by now, is control of the surface properties. You can take kind of you can go in any semiconductor plant, and you can make features on the surface which are as small as hundreds of nanometers. You can oxidize the surface, you can put monolayers, so you can change the surface properties in the way you like them. You have a control of the structure. Now, this is a picture from my own research. And you have a porous material here, which is about the holes of which are about 1 micrometer. And it's a three-dimensional porous material. Now, we are far away from really being in full control of the structure. But this control of the structure allows us to make special colloidal materials. So these days, you know how to control the surface properties. We know how to control the structure. And in order to be engineers, that is kind of, I mean, do the things the way you like them, there is also one additional degree of control that we need to make. And this degree of control is control of the interactions. And this is where kind of colloidal science and nanoscale engineering is going. Just as an example of how what people can do with controlling the interactions, you can take a suspension of particles. You can make these suspensions by controlling the interactions, form an uniform type of array. You can deposit it on a coating. You can aggregate it in loose aggregate, or you can aggregate it in dense aggregate. And you're going to have materials of different properties. So we're learning how to control the interactions. This is a very important aspect of the colloidal and nanoscale science and of nanoscale engineering. Now it's least developed, we have lots of things to do. And just to illustrate why do we have lots of things to do, if you think about biological structures, all biological structures self-assemble because the interactions between the molecules make them self-assemble in this specific structure. So hopefully one day, by nanoscale engineering, we would be able to make many, many more complex materials, structures, and devices that we can do today. But even today, we can say that we have a big degree of control. We know how to do that. This is a multidisciplinary science, so that's why we have the nanoscale engineering part of our class. And hopefully, this research is going to develop further in the future. So much about nanoscale engineering. In the last minutes of the class, let's discuss the logistics. What we have here is, this is a lot of text. I kind of wanted to illustrate how this class is going to go. It actually has 3 parts. This is the basics of the lectures. Kind of what we're going to start with from the next time is the surface properties of material and surface tension. Then we're going to start studying the molecular forces, interactions, dispersion forces, and so on, the first part of these forces. Now, what I would like to do in this class is I'm speaking a bit too much eventually. So instead of me speaking all the time, I would like to give you the floor occasionally to kind of discussions on interesting new types of topics and so on. So we're going to have discussions on interesting new technological applications of what we have studied. What you're going to do is you're going to pick up, now I have made a list of topics, it's not posted yet. I have a few pages here kind of for your preview if you like. There will be 5 discussions in the class. So each of you in about a week or 2 is going to pick up one topic which he or she finds interesting. And then I have posted also on the website, I'll show you. I have posted about 100 or so selected recent research papers. You can access these papers, you can read them. The idea is not for you to kind of read all those papers and understand what's going on. The idea is that kind of like I tell you something which you find interesting. Now I'm telling you about foams or for example foam films. You would like to read a bit more about foams. There are a few papers which I have posted about foams. So you say, well, I want to know what people are studying these days. What are they studying in foams? Are they studying the color of the films or are they studying the stability or the structure and so on? So you can go check out these papers, then go on from there, read a few more papers and so on. But once you pick a topic in one of those discussions, you are going to have the floor with a few transparencies, slides which you're going to make. Just kind of tell everybody, including me, what is the new interesting developments in this area which people are studying these days. So depending on your interest, you can pick a topic. The first discussion will be on wetting, capillarity, and surface modification, which corresponds to this first part of the class. We go through surface properties. We start with the molecular properties. We have a first exam here, just to kind of get some feedback on how well you have studied this area. All exams are going to be open notes, open books. So you can use whatever you like. Kind of the homeworks are kind of not going to include something that you need a spreadsheet, for example, and so on. In principle, all the problems will be, you can solve them with a pen and a paper if you like. Of course, if you want to use something more complex, it's up to you. So kind of the idea about exams would be more or less to try to apply what we have studied in something new problem rather than kind of having some tedious, complex calculation. So then we go through the second part of the class, where we're going to study electrostatics and understand how the interactions control the properties of colloidal systems. Now, people these days are very, very much interested in new types of interactions and in biological interactions. So that's why the second discussion is going to allow some of you to kind of like tell the others what we have learned about the new developments in biological interactions. DNA interactions, protein, lipids, bioarrays, and similar things. Now, internal interactions are not enough. I mean, we have to know how to manipulate the colloidal systems. And you can manipulate them by using electricity. So we're going to study then how we manipulate systems by using electrical voltages and currents. And then we have the second exam here, which is going to cover these parts of the class. And the third part of the class, now, I mean, it's kind of different in the sense that we're going to study areas which are more for your information rather than kind of something that you need to know just because you have graduated NC State, for example. So we're going to go through optical phenomena, light, X-ray, neutron diffraction, important methods by which you study colloids, microfabrication, microfluidics, 2 lectures. These are very important applications of colloidal science these days. Self-assembly, photonic and electronic materials. And this part of the class is going to have 3 discussions. The first one is how you use external field in order to make new types of materials and structures, or new types of devices. The second one will discuss, you have heard about nanowires, carbon nanotubes, buckyballs, quantum dots. All those are colloidal particles. So we're going to have a discussion of what these types of particles are, kind of. What are their colloid properties, how people use them, and so on. Again, you're going to have the floor mostly there. And finally, we're going to have a discussion general on nanoscale engineering. We're going to discuss, for example, kind of, I mean, is it likely that soon people would have nanobots kind of going through your body and so on, if you have heard this type of publicity aspects of nanoscale science. So we're going to kind of, I mean, knowing what we have studied in this course, we're going to discuss such issues about the future applications in what we have studied in science and technology. And obviously, kind of, I mean, I don't want to kind of evaluate how well you have studied this. What I'd like you to do at the end of this class is to learn new things. So what you're going to do is at this time of the class, you're going to kind of like instead of final exam, write short-term papers, which can be, to make it things simpler, can be an extension of what you have done during the discussions. So right now, in a couple of weeks, you're going to pick a discussion topic. You're going to read a few papers, tell us here what you have learned, and then you can read some more papers and write a short-term paper at the end of the class instead of final exam.
On the discussion days, will there be 3 or 4
Coffee or?
will there be 3 or 4 people talking at
Yeah.
a given period?
Yeah, I'd like to kind of like have more or less an even distribution of the people through discussion days. So we're going to give the floor to a few people, as much as time permits. Everybody is going to show 2 or 3 slides, which are going to be based on the literature. So we have to read papers, digest them kind of in a creative way. I mean, you're not only going to tell me that's what I read in the paper, you're going to tell me, well, I read this paper, but this paper looked very interesting. And this paper looked interesting, but I'm not sure that it can really find applications. Now, we won't be able to include our distance education participants in the discussions, but they're still going to write their short-term papers, and hopefully kind of will have the opportunity to discuss similar interesting new elements with them by the end of the class. Now, any questions about the logistics? I would like to show you, we have seen the web page. I would like to just point a few items about the web page. And that's going to finish the class. But before I do that, kind of, I mean, like, any questions about timing, discussions, short-term papers, tests.
Actually, I have a question about the books.
Yeah.
Are they both required? $200 worth of books.
Yeah, kind of. I mean, like what we're going to do is kind of. I mean, like the problem is that there is no good book which covers all that class. This book is Revashvili is good in interactions. This one is good in general colloids. Now, what I can kind of borrow my books for a limited time to anybody who would like to get them. Now, what you could do eventually is you could combine kind of in pairs or something like that, and each buys one book. You are not going to need the two books at the same time. Eventually, if you follow on the lectures, you may not need the books at all. But I would recommend that I wouldn't recommend that you buy the two books right away, but I would recommend that you find a way to be able to use the books throughout the semester. Now, again, to be truthful, the books would be required only for the first 2/3 of the class. The last kind of part of the third part of the class is really only kind of new elements which you can read in the papers and so on. Yeah.
Just had a question. Can I have these on reserve at the library by chance, or 2 copies of the books on reserve at the library?
I think the library books are already taken.
I can take them back and you can put them on reserve.
Yeah. Yeah.
I was going to use your books then.
Or we could just recall them from
Yeah. And again, I have 2 copies of the books. So I would be willing to share my copy with anybody who needs it, provided that he or she returns it in time so everybody else can use it. But kind of, I mean, if you need the book and so on, you can walk in my office and ask to borrow it if it's available. There are many other good colloids books, by the way. I have picked these 2 because this is really the standard for interactions. And this is a new book which is kind of getting to be well known in the field. This is maybe the only recent colloids book which kind of addresses the issues which we want to discuss here, where physics, chemistry, biology, and technology meet. So these books really try to cover the multidisciplinary interests that we want to cover in this class. Again, you can use the reserve, and you can use kind of my personal reserve in a way. And I'm going to try to make the web page as useful as I can. If you go to the web page, now I have what I have to do. That won't work in this way. Sorry that you have to go through all of this again. Kind of, this is a very quick review for your information. Web page. Angelica doesn't want to see this, I'm sure.
It's so tiny.
You should kind of check out now. On this computer, it really looks kind of tiny and so on. Now, you have the lectures by date. You don't want to see that. Anyway, you have the lectures by date. Now, each lecture is going to have notes, homework, solutions. If you click on this link here, this computer is kind of... Now you're going to get in a new window, what should open in the new window, will be the index page where you're going to have the streaming lectures recorded and available for visualizing with Real Player. So if you'd like that, I'll try to make them available for you. This seems never to kind of like... Maybe this is because actually the people would learn to download this lecture on the page already. The point is that I'll try to make, I don't know how this works, but I'll try to make also the streaming lectures available for you. So this is also, of course, about the distance education students. You can download the lectures, open them, you can turn on the streaming video and you can go to the lectures again if you like, kind of following everything that I have said on the slides. Again, like I mean, let's see what will happen now. Again, the web page, when it will begin to look properly, you can have the guidelines and policies. I would ask you to read them, so you should know kind of what's required for this class and so on. You have my address here. The discussion topics will be posted on the page. So next week you'll be able to go there and kind of start thinking about what discussion topic you would like to have. You have a variety of useful links which link you to surfactants, colloids, photonic materials, and so on sites. And finally, you have references, which would be where?
It's hiding on the G. It's right there, isn't it?
Well, it should be here, kind of, I don't know where it's hiding right now, but you also have a link to a page which is going to hold the links to the 100 papers that we have downloaded.
Additional readings. That's the link that is not shown.
Yeah, I mean, you kind of, anyway, we'll fix that. I mean, kind of, we have done this in a day and a half, so kind of, we haven't removed all glitches yet. Takao found out that when you try to download the lecture, it may not download the first time. So what you do is you log in, go back and try to download it again, and it would download. So it's going to be there kind of a few hours before the class usually. The notes will be there. The homeworks will be posted. Kind of, I have also given a few copies of the recent homeworks. So you can also download the homework. Now homeworks, this does not relate to the distance education students. Now homeworks work like that. The homeworks will be posted on the Tuesday of the week of the classes. So kind of by Tuesday you can download the homework if you like. And they are due next Thursday in 10 days. So kind of, let's say this week we're studying electrostatics. The electrostatics homework will be available by the lecture on Tuesday. We study electrostatics through the week. Next week on Thursday, you have to turn in the electrostatics homework. For the auditing students, I have put in some requirements. They have to do at least half of the homework problems. So they can just kind of get also kind of, if you don't do some hands-on work, it's really not going to help you too much. Of course, the auditing students are excused from the test, but they have to kind of try to solve the test themselves. And the short-term paper is kind of, we'll discuss this when the short-term paper comes. Okay, let's finish the class formally. We're due past the time, and we can take a few questions later.
How are we submitting the homeworks?
Sorry?
How are we submitting the homeworks?